So what we can infer from this equation, rho equals to na cube e to the power minus bc square. Okay, so we can infer from the equation rho equals to na cube e to the power minus bc square. The first thing is that molecular density which is number density, molecular number density which is rho, depends only on the velocity c. Okay, so if you look at this equation, n is the total number of molecules in a gaseous system which is constant for the system, and a was the integration constant which is also a constant, and b is alpha by 2 which is alpha is undetermined multiplier, a constant. So what is the variable in this equation? The only variable is c. So the number density, molecular number density varies only with c, that is it depends only on the velocity c. So if you put different values of c, you will find that different number of molecules per unit volume are moving with that particular velocity. Number 2, the distribution of molecules is spherically symmetric in the velocity space. Now, as this number density depends only on c, if we draw a sphere of radius c in this velocity diagram. Okay, so this is our velocity diagram that we have already used before. So if we draw a sphere of radius, so this is a sphere, okay, in 3D imagine it as a sphere. If we draw a sphere of radius c, then every point, so this is a sphere of radius c, so every point on the surface of this sphere, every point on the surface of this sphere has same value of number density which is rho. Okay, because rho depends on c, only on c, so for a same value of c, rho will be same, and every point on this sphere has same value of c, which is the radius of the sphere. So every point on the surface of the sphere has same value of number density, that is the number density is spherically symmetric in velocity space. Okay, so it is spherical symmetry in velocity space, velocity diagram. So it leads to another conclusion that the distribution is isotropic. Now the distribution of isotropic, what does it mean? It means that no matter in which direction you measure, you go up to a magnitude of c in velocity space, the value of rho, that is number density of molecules, will be same. You will find that no matter in which direction you go up to a magnitude of c, you will find the same value of the molecular number density. That is, suppose you go in this direction up to a magnitude of c, suppose you find value the number density to be rho 1, and here you go in this direction and you find the number density to be row 2. You will find that these two are equal, which is equals to row. So row 1 equals to row 2 equals to row which is n a cube e to the power minus b c square. So if you go in this direction, you will find that over here also the number density is row. If you go in this direction up to magnitude of c, here also you will find that the number density is row. It means that no matter in which direction you measure the physical property, the property of number density of a gaseous system in a velocity space, it will have equal value in same value in every direction. That's why it is the distribution is isotropic. Okay. Now the number third point is that rho falls off exponentially with c. Now if we plot rho against c, the plot will look like this. So along y-axis we plot rho and along x-axis we plot c. So the relation is this, n a cube e to the power minus b c square. Now if we plot this, if we represent it graphically, then it will look like this. That is, rho is decreasing with increased value of c exponentially. Okay, it is decreasing exponentially. And at c equals to 0, rho is n a cube. Okay, so at c equals to 0, the value of number density is n a cube. So at c equals to 0, value of rho is n a cube.